All right. Okay, so for DOS, as you know, there we have parts of DOS, steel part and concrete part. So the steel part we are being taught by Sir Rashid and membrane. So the part of membrane is all theoretical. There is no numerical in this part in mid course. Final course we will have design of concrete deck slab and all that bridges, steel bridges. For mid parts there is no numerical in membrane part, but there are two in topics. Major topics is Sir Rashid. First one is beam column, and the second one is base plate. So we'll try to through these two topics, and if we have time, we'll try to cover the concrete part also. So concrete part, we have two major portions. First is residential building, and the second is industrial or commercial building. So if you see the past papers, for concrete part, it's simple. Simple questions are asked, like I think structural scheme was asked before. Draw a structural scheme. A house plan was given, and we have to draw a structural scheme. So that was asked, and design of slab was also asked. Two-way slab by ACI coefficients method. That was asked, and for industrial building, I think the factors used in seismic design. In ETAP, we use different factors for seismic design. So these factors were asked. Like if I can show. So only the name of these factors were asked. Because we have not done any design in this till now, the mid course, so only factors were asked. So this concrete part is relatively easier than steel part, so we'll try to cover the Rashid part first. Okay. The first is beam column. So as its name suggests, it is a combination of beam and a column. We know that a simple beam is subjected to suppose vertical loading. So it has shear force in it as well as bending moment. So a simple beam has shear force and bending moment. And for an axial column, so this is a perfect column. It is only subjected to axial loads. So there are only axial loads in column in ideal conditions. Only axial loads in column and only shear and bending in beams. So these are two separate things, beams and column, and their design are different. But for a beam column, it is a combination of beam and column. Combination of beam plus column. So if we combine both beam, for example, if we have a column, it is subjected to both axial loads as well as bending moment or shear force. Normally there is where the shear force, so we can say that if a column is subjected to both axial as well as bending moments, if there are both axial stresses present in it as well as bending stresses, so that structural number we call as beam column. All right. So if they are both axial as well as bending stresses, that is a beam column. So one moment. So if we go to this, select anyone. Go to define and load patterns and just define a seismic one. and based on SCE. So if you go to modify lateral load, so these factors we have to memorize. This one CT, first one is CT, second one is SS and S1. These are both uh, factors based on the longitude and latitude of our location. So the SS and S1. These are we have to just memorize these names. So we have to memorize CT, SS, S1. If we have to go CT for time period, as you know the formula for time period is CT times HN power 3 by 4. HN is the total height of the building. So we have to memorize the CT, SS and S1, SS, S1, and FA and FV. These are dependent on the soil class. If we change this class, this FA and FV would be changed. So if we write soil class only, then automatically it will select FA and FV. Furthermore, SDS and SD1 will automatically be selected R omega CD and I. R omega CD and I. So we have to remember the names at least of this, the CTS and S1 and soil classification or FA and FE and R omega CD and I. So these factors are required for CNA design. We check a past paper, these were asked. So that was split out. So for beam column, if a structural member is subjected both axial load as well as bending moments, then we call that member as a beam column. So this was a beam column. We are going to design it. The next question is from where this bending moment comes in columns. Because usually the columns are usually the slabs are resting on column, so only axial load is transferred. So where this bending moment comes. So there are 4 or 5 reasons for bending moment in columns. So the first one reason is that if the column is not initially perfectly straight. For example, this was the center line. This is the vertical line. If a column was constructed a little bit uh, initially imperfect, or you can say it was not initially vertical, a bit it was leaning to one side. So this load and this eccentricity. This load will have some eccentricity from the center line, and the bending moment would be P into E. Bending moment would be generated, which would be P times E. So it would be like this bending moment. This load would this load acting at some eccentricity would produce a bending moment in column. That so the first one is the column is not initially vertical, perfectly vertical. Second reason can be that there is some initial imperfection or initial crookedness in column. So, for example, a column is like this. It is initially imperfect. So when we apply the load, there would be some eccentricity to this load. So this would generate another bending moment. The third reason can be the moment can be transferred from beams. For example, this is a column and this is a beam. They both have a rigid connection. For example, they are both monolithically casted or they are steel going from beam to column. So this steel would transfer bending moment from beam to column. So whatever the bending moment would be at beams, at the ends of beam would be transferred to column. So this would produce a moment in the column. Another reason could be that if this is a column, sometimes brackets are provided in columns. This region is called bracket. Why these are provided? Because beams are rested on these brackets. If the column is very high, we cannot rest. We are going to cast a very high column in one row. So for resting the beams, we cannot rest the beam at the same times. So sorry, we cannot cast the beam at the same time. If so, we provide brackets in column So in the future, if it requires the beam, we can cast beam on it. So these brackets, they applied moment like load like this. So this load is quite a bit away from the centroid of column. So it would have a high centricity. So it can be that brackets in column, they cause bending moment in the column. So these are 3 to 4 reasons why there is bending moment in column. It can be asked in quiz. Afterwards, we have second order effects. What is second order effects? For example, if this is a column, it is only subjected to axial load P. So if we analyze this, that we'll get that this column would reflect by small amount delta, and we get if we analyze the column only using the axial load P, we'll get some deflection of column as delta. That we'll know that the column would reflect by only 1 millimeter or 1.5 millimeters, something. This is the first order analysis. First order analysis. First order analysis is if we only check the column or analyze the column for axial load. That only we check the column for axial load. That only we are checking the stability or safety of the column for axial load. This is first order analysis. But second order effect. For example, this load causes and deflection delta. So in a real scenario, suppose this column has reflected by amount delta from its original position. The load now is acting as some eccentricity from the original position. So this load would cause a bending moment that would be P times delta. So this is called second order effect. That the load which was not initially causing any bending moment in the column. It was applied exactly at the center of the column, center line of the column. So it was not causing any deflection, any bending moment, but it caused some deflection in the column, and that deflection led to generation of bending moment in the column. So we call this moment as second order effect. This moment is generated due to the deflection caused by the axial load. So this is called the second order effect or P delta effect. Those are the same thing, and this causes moment magnification in the column. Why? Because uh, even if the deflection is like 1 or 2 mm, very small deflection, but the load on column, for example, it is a 10-story building. So all the load from all the stories is coming on this one column. So the load is very high on column. So even very small deflections when subjected to very high axial loads. So this the product P delta is very large. So this large product means very high moment. Moment is very high. So this can cause the column to fail well before what we anticipated. All right. So this is P delta effect. It can also be like this. For example, this is a one-way uh, column, one-way structure. It is being acted upon by some lateral load. So this would cause some side sway in the column like this. So this is deflection in this. So for example, if the initial load was acting vertically, now it is at some eccentricity. It was acting vertically, now it is some eccentricity from the original motion. So this is again causing bending moment. M is equal to P times delta. And this delta is very large as compared to this delta. So this case is more critical. All right, any issue up till this part? This was all the theory before we jump into the question. Any problem?
Brother, Can you once
Yes.
explain what is the major difference? How the second order and first order effect will differentiate both of them?
First order effect. First order effect is only due to axial loads. For example, this is a column. This is some load. Or also, we can apply this. This moment is coming from beam. So we know that this load and this moment is coming from beam. We calculate deflections of column. We calculate axial stresses in this column, shear stresses in column, and even bending moment. Because there is bending moment, so there will also be shear and there will also be bending moment in this. So this is first order effect that due to originally applied load, we are calculating the deflection and response, basically the response of the column. What is the response of the column to the initial load? This is first order. Second order is that due to the first order loads, due to the structural response in order, due to the structural response after the first order loads. For example, due to this load and this moment, the column is deflecting like this. In first order, we were considering the column is in exactly straight and all this. That is, there no eccentricity and everything. But in second order, we are considering that the column has reflected. It is like uh, when we are casting the column, that is first order. That at time is equal to zero. That only load is present is axial load or moments. But after some time, the column has deflected, and due to this deflection, this delta, the load which was initially supposed 1000 kilonewton, the reflection is 2 millimeter, and moment was 50 supposed. Initially it was 50, but now the moment would be 50 plus 1000 into 2. So the moment would become 2050. This is second order moment. That due
Okay,
to that this moment has been added, almost 2000 moment has been added. So this is very high. We have to consider this. Otherwise, the structure would fail well before what we thought. All right. So should we start the
yes.
question?
Okay, brother.
Okay. So let's go. So it is. They are asking that design the columns in a single bay multi-story unbraced frame. So for example, if the even if the page is not given, we can create it. In this question, they have given this image, but if even if in the paper only the statement is given, we have to make the image from this. So they are saying single bay multi-story frame. Single bay means columns like this. So this is single bay. And the second is multi-story. So there are more columns over this. That it is multi-story building. With FR is friction resistance. So we are ignoring friction, and P is load from top story. So they are saying that P load is applied from top stories. That load P is coming from top stories. And the ratio of moment of inertia to beams to with respect to columns AB is 0. So the moment of inertia of beam is 1.4 and the columns is 1. So we can write it 1.4i and 1i. So simply we can write 1.4 and 1. The uniform dead load and live loads are this UL. So let me write a moment. So PD is point dead load, PL point live load, omega D uniform dead load, omega D uniform live load, and H is the wind load. H is the wind load. Dead load is 1025 410. 10.3 22 345. 10.3 22 So these are all loadings. Loadings. So we have to design this for this. They are saying that assume that the sway is not allowed in y direction. So what is sway? For example, this is a column. So usually the axis, this is an I section. The major axis for this I section is this one, which is parallel to the flanges. The axis parallel to the flanges I section is the major axis. Why it is a major? Because Ix, the moment of inertia about this axis is much higher. You can see it from the tables also that Ix for, they're saying that for I section this is the x-axis. The moment of inertia for this axis is 866, while Iy is only 33. So Ix is very much higher than Iy. So we call this as major axis, x-axis. While y is the minor axis and it is like this. Is it parallel to web? So for I section, always the major axis would be parallel to flanges, while the minor axis would be parallel to the web. So they are saying that assume that sway is not allowed about y direction. So for example, if our column is placed like this is our column. So what would be our x direction, which is parallel to this, parallel to the flange of the section. So this is our x direction. Y direction in this way. So this is our y direction. While the z axis is vertical axis, so it will be like this. An issue in this, that what is the major axis and what is the minor axis, because the next part we are going to use this. Okay, so they are saying that assume that the sway is not allowed about y direction. There are two words here, about and along. For example, about. Just remember that movement is always about an axis. That for example, this is a y-axis, so movement would also always be about this axis. So my. So movement about y-axis is my. The movement about x-axis is mx. So if they are asking that about some axis, spoken about y-axis, that means my. There and what is affected by my? Just remember a1y, a2y, and ly. These all quantities would be affected by this about my, about y-axis. Okay, and for along this is opposite. For example, if they are saying along y-axis means about x, and so movement would be x-axis. This is y-axis, this is x-axis. They are saying along y-axis. This is along y-axis. So for along y, what the movement would be about mx. The movement would be about x-axis. Okay. So the quantity factor would be k1x, k2x, and fx. This is just focus on this. The problem in this that what about and what along means.
Let's go ahead.
Should we continue? Because this is very important. The whole question depends on this. That if we assume opposite values for this, then all solution would be wrong. So they are saying that assume that the sway is not allowed about the y direction. So about the y direction. So what does that mean? What would be affected? My. Okay. That they are saying that sway is not allowed about y direction. About y. So my would be affected. That means k1y, hmm, k2y, and ly would be affected. And what would be effect? They are saying that the column is braced at mid depth. That, for example, this is a column, they are bracing at mid depth. So if the column height was 6 meter, then Ly would be 3 meter and 3 meter. All right. So we are going to reduce Ly, not Lx, because the bracing is about y axis. And another thing of bracing, if the column is braced in any direction, then in that direction there will be no little movement. So k2y would be so k2 would be 0. It can be k2x or it can be k2y. Whichever direction it is braced about, then there will be no second or lateral movement in that. So any problem? Hmm? So
The 1 by and
Uh,
2 by
bro-
representation.
yes,
brother, can you please explain again that about K2, how it is going to be 0?
k2. So for example, yes, k1. K1 we call it as this is effective length factor for no translation. That there is no lateral movement. Then the effective length factor would be K1. K2 is a effective length factor for lateral movement or lateral translation. Lateral trans. So if they are saying that the beam is braced about y direction, that the beam is braced for this is y direction, and there is some bracing over in this direction. That the beam is braced, there is no lateral translation. So if there is no lateral translation, that means this K2 would be 0. Okay. That there
Okay,
is
bro.
no lateral translation. There is no translation. So if there is no translation, that means that there is no even movement would be 0. My would be 0 in this case. That there is no movement in this direction. We are stopping that. Fine.
Fine, brother.
Okay. So this was all the question. First step. First step is to define load combinations. You have to define load combination. They may or may not be given in the paper. So we have to memorize these two basic ones. 1.2 dead plus 1.6 live. This is our first load combination. A second load combination is 1.2 dead plus 0.5 live plus 1.3 wind. This is for wind load. So we have to memorize these two basic ones. Sir was saying that if some other load combination is required, that would be provided in the paper. You have no need to memorize that. And these are also present in LRFD design 8. We go here. So many these load combination are present. This one is 1.2 dat plus 1.6 light, 1.2 dat plus 0.5 light plus 1.6 wind. So we are using 1.3 wind here. So just memorize these two ones. Any extra one would be given in the paper. So these we have to use these two load combination. So for first load combination, we have to define PU, that would be 1.2 PD plus 1.6 PL. Omega U is equal to 1.2 omega D plus 1.6 omega L. Just this load combination, we are applying both axial load as well as UDL. Distribute. Okay, so this way we can get PU and omega U. The third thing we have to find is notional load, NI. So the notional load is 0.002 alpha into YI. Alpha is 1.04 LRFD, which we are going to use LRFD design it, and 1.6 for ESD. We are not going to use ESD, so alpha would be 1. So alpha is 1. YI is the total gravity load. Total gravity load. So for example, this is our column. This is our frame. The total gravity load would be PU 2 times PU plus omega U into this distance. Okay. Total gravity load would be times PU, these two loads, plus omega U is UDL times length. This would be total gravity load on the frame. So we'll use YI as this one. And why we are using 0.002? This is because we are assuming notional load. Why we are applying notional load? Because we are assuming ourselves that the column is not perfectly straight at the start. It is initially imperfect at a distance of L by 500. So this L by 500 we are assuming as a factor of safety, that the column is not initially straight, perfectly straight, and it is a little bit deflected. So if we calculate this L by 500, it would become 0.002. So this 0.002 comes from here. This 0.2 comes from here. If they are saying in the question that the column is deflected at 1 by 600 or 1 by 1000, then we are not going to use this 0.0. For example, they are saying that the column is deflected at 1 by 1000. Then we are going to use 0.001 or 0.001. Whatever the factor they are given, we are going to use here. Okay, this will be notional load. This is for our load combination 1. Next, we have to do the same thing for load combination 2. Just the factor would be different. PU would be 1.2 PD, 0.5. This factor is different. Omega U is 1.2 PD plus 0.5 EF, and because we have wind load in this combination as well, 1.3 W, we'll use H is equal to 1.3 into HU is equal to 1.3 into whatever the wind load was. This is the load combinations. This is the last one is notional load again. We'll use this notional load in every load combination. 0.00 into alpha into y. Y would be times PU, this PU plus omega U into L. This PU and omega U we'll use for this YI, and this PU and omega U we'll use for this. Each load combination would have its own YI. Any problem in this part? For that first step. The second step. After we have defined a load combination, we have to analyze. We have to analyze our structure. Yeah, this was our frame. We know now the PU and omega U and as well as HU. So we have to analyze our structure. So what load combination would be? We can use both load combination. The critical one, the critical load combination, we'll have always have to select the load combination which contains a lateral load. Whichever the load combination contains a lateral load, always be. And if there are two or more load combinations containing a lateral load, so we'll select the one which has the highest lateral load. Highest lateral load which cause highest moment. One with highest lateral load will select which only cause highest moment. We can analyze for both load combinations, but for simply for faster work, we can directly use load combination 2 because it contains the lateral load. Load combination 1 has no lateral load. So to analyze this frame, we have to go to here. This is page number 280 of LFD. So there are few frames given. We have to select one on the basis on our load, whichever is the load. So this load is UDL. So we'll divide our frame, this frame. This contains UDL point load as well as the lateral load and notional load also. Notional load is also a lateral load. It is applied as a point lateral load. So we'll divide this frame into three parts. That first part contains only UDL. Thus the second part contains only this wind load. The third part contains only notional load. So we'll carry out three separate analysis for this. For UDL, we'll use frame 1. I write frame 1 here. For notional as well as wind load, we'll use frame number 6. This one. This frame we'll use for, we can see that point load is acting. So we'll use frame 6 for both this one as well as this one. So for analysis, just we have to find out these factors. P is equal to I2 or I1 times H over L. H is given as column length, L is the beam length. So I2 or I1. I2 is the beam and I1 is the column moment of inertia. So we know that I2 is 1.4 I1 is 1 I, or I times H is, we know that it is 6 meter, L is 8.5 meter. So we can find K, from K we can find N and N1 and N2. Okay, so these K and 1 and 2 are used in all cases. So these remain same in every case. We have to only calculate them once. After calculating K, we have to find MA, MB and VA. These three things. MC and MD we do not require. They are exactly same as, this would be same as MB and MD is same as MA. Only the sign are different. So we have to calculate MA, MB and VA for all these cases. For frame 6, we have to calculate 2 times. First we apply this wind load only, and second we apply only notional load here. So we have to find MA, MB and VA for gravity, MA, MB and VA for wind, MA, MB and VA for notional load. Whatever the sign was, we have to ignore this. For example, this was 50, this was minus 100. So we have to ignore the sign. We have to select the largest moment. We select this 100. This was 100, this was 50. We select this one. And this was 50 and 75. We select, this would be 5 or 7.5. We'll select the larger one. Notional load moments would be very small. And similarly, we have to ignore the sign of reactions. Just take the magnitude. Whatever the magnitude was, we have to take this. This is the second step. We have to analyze our column frame 3 times. 2 for this and 1 for this gravity loading. And remember, these are for fixed port. These formulas are given for fixed port. If the port is hinged like this, so we'll use this formula for pin base. The top ones are for fixed base and the bottom ones are for hinged base. No, we do not need HA or actually these are no. Okay, and if the wind was not given as a point load but as given as a lateral uniformly distributed load. This is a laterally uniformly distributed load. Then we'll have to use the frame 2 for that. Just depending on how the load is presented, we have to use that frame. Okay, an issue in this was the second part. Okay, the third one is we have to determine the K values. For example, this is our column. We know this point is A, or this point is B. So we have to determine the K value or K is effective length factor. So as we were discussing earlier that there would be two K values, K1 and K2. K1 for no side sway, no lateral or no side sway, K2 for lateral movement. And these K1 and K2 would further be divided into two parts, K1X and K1Y and K2X and K2Y. Actually, there are four. So as there was bracing about Y direction, so we said that there is no K2Y. But there were no questions of bracing about x-axis, so K2X would be present and K1Y and K1X would also be present. So for first of all for K1X, if we go to here alignment charts, these are the alignment charts. So the top one is for K1. This alignment chart is for K1 and this alignment chart is for K2. This is sway allowed for K2 and this is sway prevented for K1. So the formula is we have to calculate psi A at point A, psi B at point B. Psi A at point A, we have to determine psi A here and psi B here. Then we can use whatever the values were, we can join them and we can check what is our K value. So this is how we are going to find our K value. So at A point we have a fixed port. So for fixed port, the psi value is directly given. The psi value is 0.5 for fixed port as well as for braced. So K1, we were saying that K1 is for no lateral or braced, same meaning. It is braced. That K1 has no lateral translation, so it is braced. And for K1X, psi A would be 0.5. Okay, for fixed port as well as braced. Psi B, so for psi B, we are going to use this formula. EI over L of columns over EI over L of beams. So at psi B, we know there is another column on the top and a beam in this side. So psi B would be EI over L of columns. E is this, I is I, and column length is 6. And as there are two columns, so we multiply it by 2. For E into beam's moment of inertia is 1.4i and the length is 8.5. So if we solve this, our value comes about 2.02. So we have psi A and psi B. Psi A is 0.5, psi b is 2.02, almost 2. So if we join them, so our K1x value would be 0.7, 0.75, almost 0.77. So K1x is equal to 0.77. And we'll round it up to 1 because we are not going to use any value lesser than 1. We conservatively round it to 1. Any problem in this? Write with charts. That how we are going to use these. The second one is K1, K2x, K2x. So for K2x, as we were saying that K2 is for sway loud. So psi A would be 1 in this case. Apart from we'll that use psi A as is a fixed port and sway is allowed. So psi A would be 1. Or import these formula, these values as well. And psi B would be same as the same beam and columns are present. So it would be 2.02. We'll check this one here. 1 and 2.02, almost this. So if we join them, almost 1.123, 1.45. We'll use K2x equal to 1.45. Okay. So again, we have to find K1y because there is no information. We are only given information about this 2D frame. There is no information given that there are beams in into the page or something, columns in that direction also. So we are going to assume K1 is as 1.0. Assume. If there is no information given that we are, then we will assume K1 as 1 and K2 as 1.2, 1.5. Any value we can. So K1y we are going to assume 1 and K2y is 0 because there is bracing in that direction. Because of bracing there is no little movement. So K2y is 0. If there was no bracing, then we could assume K2y is 1.2. Okay, this was the third step that we have to find the factorial factors. The fourth is selection of trial section. Selection of trial section. How we are going to select trial section. For this, the formulas are given here at the end of the book after chapter number 4. So these formulas are for chapter number 4 and this is for chapter number 5. These are the interaction equations. These formulas. We are going to use this formula for trial section. This is P equivalent is equal to PR plus MRX MX MRY MY. P equivalent is equal to PR plus MRX MX plus MRY MY. Because there is no movement in about y direction, so this is 0. For PR, PR is simply the sum of all the directions. We calculated VA in 3 VAs, so we'll simply add them. Plus VA from this, plus VA from this, plus VA from this. So VA from gravity plus VA from wind plus VA from notional. So we'll simply add them irrespective of those signs. Whatever the signs are, we are going to assume them as positive and add them. So this would give us PR or applied force on our PR is applied force. Second is MRX. MRX would again simply we calculate two moments, MA and MB, MA and MB, MA and MB. So whichever is the largest of these two, we'll select. So for example, MB from here MA, from here again MB. So we'll select the largest without their sign. So I can write that MA or MB, whichever is the largest from gravity, plus MA or MB, largest one from wind, plus MA or MB from ocean. And sign is always all positive. Whatever the sign are, take all of them as positive. So this way we can get PR and MR. For MX, these formulas are given. That for MX, for first trial, it is 8.5 minus MX is equal to 8.5 minus 0.7 K1x Lx for first trial. We are doing the first trial, so we'll use these formulas first. So we know that 8.5 minus 0.7 K1 was 1 and Lx was 6 meter. So we can calculate M like this. So it comes about 4.2 or 4.3. So this is our mx. So we'll simply use this equation again. P equivalent is equal to PR plus MR x into mx. And we have to remember to use 1.15 factor here. Why? We are assuming that the second order moments would increase the first order moments by 15%. Assuming this, we are assuming this. This analysis, we carried out this analysis. This was first order analysis. We do not use any magnification factor here. It was for first order analysis. Now we know that for second order the moment value would increase. So we'll assume that almost 15% moment would increase. So we'll multiply it by 1.15. Okay, so this is how we can get P equivalent, and we'll for P equivalent and we'll use KY LY. KY we know 1, LY is 3 meter. So because in y direction, about y direction, the column was braced at midpoint. Towards unbraced length is 3 meters. So KY LY is 3 meter and P equivalent is almost 5908. So these values we have calculated 5908 and 3 meter. We'll have to take these values and go to column selection tables. This one, column selection tables. We'll start from the last page of this. These are for 345 megapascal. We are using 250, so these are for 250 tables. We'll start from last page of these tables and go in the left directions like this. At 3 meters, we have to check what is our column must check capacity of about 5900 kilonewtons. So it is only 265 and 312 here. We'll go to the previous page. At 3 meter it is 903 only. Again 3 meter 24. 3 meter 2293. At 3 meter 2000. There was 4000 value here, but still not about 6. We require about 6000 kilonewtons. So 3 meter we have 4100. And here at 3 meter we have 6000. So the first we can select our first section as W310 into 226. The first one would be W310 into 26. Then we have to check other sections also, because we have to select the lightest one because it is the most economical. We'll check all the tables. For 3 meter, all are heavier. 3 meter, no lesser capacity. Almost for this was 5,000. And this one. For 3 meter, we have capacity 5905. So our required was 5908. Almost it is equal. We'll use W360 into 216. So this is almost 10 kilograms lighter. This is weight in kilogram per meter. So this is almost 10 kilograms lighter than W3101 per meter. So this was the second section. We can check for our third section also, very heavy. And so we have selected two sections because this is the lighter one. This would be our first trial section. It's like the lightest one. So for this section, we'll have to check the D value as well as Rx or Ry ratio. These two things we have to check for this column. So this was the column. The Rx or Ry ratio is this 1.59. This one, this column. Rx or Ry is 1.59. For D value, we have to go to the starting pages. This W sections. We have to find this section W360 into 216 here. 840, 690, 610, 410, 360. This is 360 into this is W360, this is 216. So D is 376. This is D, depth of section. 376 millimeter. Okay, so we have selected D and Rx or Ry for this section. After selecting this, we have to again calculate mx and my. First we calculated for first trial section. Now we'll calculate exact mx and my. We have calculated first trial section. We have already done this. Now we'll use this formula. Mx is equal to 10 minus 14 P over 1000 whole square minus 0.7 K on x and x. So we'll put the value of D here and we'll calculate mx again. D value was this one. So we'll calculate mx here. And again, we'll find P equivalent again. P equivalent is equal to PR plus 1.15 MRX to MX because MX value was changed. So our P equivalent would also change. Then we'll select the column as equal strength column. For equal strength column, we have to find KYLY equivalent. KYLY equivalent is KXLX divided by Rx over Ry ratio. So we found the ratio for this one. For this purpose, we know that Kx, okay, we have two Kx, K1x, K2x. K1x is 1, K2x is 1.45. So we'll select the larger one. 1.45 times 6,000, so it was 6 meter over Rx over Ry ratio was 1.59. 1.5. So this way we'll get value of about 5.47 meters. So we have KYLY equivalent at 5.47 meters. We know that KYLY was 3 meters before we used here. KYLY is 3 meters, but KYLY equivalent is 5.47. We'll use the larger of this. So we'll use 5.47, almost 5.5 meters. So now we'll again go to beam column section tables, but the length we would use is 5.5 meter and P equivalent is this one. This is 5434. So we'll use P equivalent as 5434 and EYLY as 5.5. Again, here, so at 5.5, no, 5.5, very less capacity. 5.5 only 1600. 3.5400. Very less capacity is 5.5 and 3000. No, not 54. 5.5, no. 5.5 this. So we have this first section. W310 into 253. This is satisfying. First section is W310 into 253. Again, we have to check all the columns. Because you can find here the lighter one that appears 557, almost here. So at 5.5, we have this capacity 5798. So this is W360 into 237. 360 into 37. Again, this is the lighter one. This is 237. This is 253. Wait. So we'll select this as final trial section. This is again, this is still a trial section. We select this. And the properties we have to find its area, Rx, Ry, and Ix. Area is for this section, this one, 30,1000. Rx is, there is no Rx given here, but Ry is given. Ry is 102. We know the ratio Ry is 102. We know the ratio is ratio of Rx over Ry is 1.6. So we can just multiply 102 into 1.6 and get Ry. 1.6 and get Ry. Or we can check the tables, the first part of the book, and get accurate value for Ry. We can simply get approximate from this one. And Ix is this one, 79,100 times 10 to the power 4. These units are raised to power 10 to the power 4. So this is how this all information we would be requiring the following steps. Any problems up to this part? We have selected a trial section.
Brother, while we are selecting it at final trial section, we are taking the P equivalent value. The second value we have find, na? New value.
Yes, new values. New
Okay.
equivalent values, new KY value.
Okay, brother.
And if in paper the problem is only in access part, we can all skip up to this part. This would be not required. For example, in the paper it was given if that this is a frame, this is load applied on this. Section selected was W360 into 137. It was already given. So we can skip all this part till this part. This is for design part only. That is, the section was not given and we have to design it. This was the design. Now we are going to perform analysis on this part. That we are going to check, we are going to analyze whether this column satisfy our load. That is why otherwise we have to revise. So now we are selecting, we have to find moment magnification factors. Their formula is also given here. Step number 5. So B1 and B2. This one. Yeah, we have to find B1 and B2. They are moment. if in only analysis problem was given, then we'll directly start from here. Also, we have to find k1x, k1y. In that case also, that is small. Two regression factors. C1 is Cm over 1 minus alpha. C1 is equal to Cm 1 minus alpha PR over PE. So alpha we know as 1 for LRFT equal to 1.6 for EST. And Cm. Cm is equal to 0.6 minus 0.4 M1 over M2. You have to memorize this formula. It is not given in the book. It is written that we can conservatively take Cm as 1, but that would result in much high value of B1. Our section most probably fail in that case. So you have to memorize this formula. In this case, M1, we calculated 2 points from gravity loads. This is gravity loading. This is wind loading. This is motion load. Gravity loads, we calculate 2 moments, MA and MB. The smaller one is M1. Just remember that it is only for gravity loads. M1 is smaller, only gravity. That only the smaller one from. And M2 is the larger one from gravity loads. Gravity loads. Simply put in the values and we'll get same value. PR value we have already calculated. This one. This we have calculated. This one. PR is equal to summation of all the. We know that PE1. P1 is the Euler's critical load for first order analysis. E is Euler's critical load. 1 stands for first order analysis. That we are not considering this. It is simply pi square EIX for K1x x. Remember, we have to use K1 because it is B1. We are going to use K1 here. We are not going to use the larger one of K1 and K2. We are just going to use K1 here. This is pi square EIX for K1 x times LX. This way we can calculate B value. So if the B value is less than 1, we'll use B1 is equal to 1. Is also written there. It must always be greater than or equal to 1. We have to use B value in points. Okay, so this is B1. Second is B2. Second one beneficial vector is B2. B2 is 1 over 1 minus alpha coefficient P and T coefficient PE. P and T. P and T is sum of all gravity loads. Sum of all gravity loads. Why gravity? Because it is written as P and T. And T means no translation. So gravity loads do not cause any lateral movement. We are going to use only gravity loads. And remember, we are going to use gravity loads in this sections. So 2 times Pu plus again we are going to use times Pu plus omega u into x. Same as before. This sum of all gravity loads and PE2. We have this column. We have this frame. So in this frame we have 2 columns. So PE2 would be this column's Euler's critical load, that is pi square EIX or K2x LX. Remember, here will be using K2 because it is P2. And because there are 2 columns here, so we'll simply multiply it by. If there was 3 columns, we have to multiply it by 3, 4, and so on. Okay, so if we put in the values, we'll get P2. And in case that it is given that story drift must not exceed span by suppose 500. Story drift. So story drift is this thing that if this is multi-story building and it is acted on by wind load, then it would sway in this direction. So this deflection will we call it as delta H or so story drift. If it is written as story drift, it delta H it should not be greater than span over span or L by 500. So take L to this side, it would become 1 over 500. So this delta H over L is drift index, story drift index. So story drift index, this delta H over L. We can be given story drift or story drift index can be given any one of this. So if we are given this one, then we have to find PE2 by this formula. Just this change would occur that we have to find PE2 by this formula. This is Rm into delta H summation of all lateral forces. And if we take this L to the bottom, delta H of L. So this is drift index, Rm into delta H summation of all lateral forces divided by drift index. So if we calculate drift index is 1 by 500, I simply plug in 1 by 500. And Rm is modification factor for building. It is used 0.85 for moment resisting frames and 1 for all other. So if any building except for moment resisting is given, we will use 1. Otherwise, we'll use 20. If moment resisting is given, we'll use 0.85. Okay, then we can plug in this PE2 here and get B2. We calculated B1 and B2 by this. This is our fifth step. An issue in this. All right. Our second last step would be determine the capacities of. This is the interaction equation. Yes.
Show me the second equation for PE2. The Rm value.
Rm.
Yeah. 0.85 we have to take.
For moment resisting. And 1 for all other cases. It's also written in book, I think. Add it there. And also that we have to use point R, 0.85 value. 3 for resisting frames, while 1 for all. Okay.
Okay, brother.
So our second last step would be to calculate the capacities of our sections. This is the interaction equation we are going to use. This one. Suppose if I write it here, then it will be like PR over PC plus MRX or MCX plus MRY or MCY. This should be less or equal to 1.0. So we have to, we can ignore MY because there is no that direction. So we have to find 4 values. PR, PC, MRX, MCX. We have to calculate these 4 values. PR. Just we have like we have done before that we have to sum formula is ENT plus B2 times PLT. Or we simply sum these outputs. Now we are going to sum them by multiplying this P2. So PNT, we know that PNT is from whatever the VA direction was from gravity loads only. So that would be our PNT plus B2 what we calculated here before step this one, and PLT is VA from wind load plus VA from motion of both. We sum them and multiply by B2 and multiply by add it with VA with gravity, so we'll get PR. Only difference in this step and PR we calculated before this B2. So we were not multiplying by B2 because we do not know value of B2. Now we are taking into the our second is MRX. Again same formula, B1 into MNTX plus B2 again this B1 we are going to use. MNTX is the largest moment of MA or MB for only gravity loading. That is no translation, only gravity loading. MLTS is the sum of the moments whatever is the P or B larger wind load plus notion whatever sign consideration. And sum them and multiply by B2 and we multiply the gravity moment with V1 and sum them and we'll get M. These were applied loads. PR and MR. These refer to applied loads. PC and MC, these are our capacities. The capacity of our section. So for PC, we are going to use the exact same method we used in the compression member design. We have to calculate the slenderness ratio first. So slenderness ratio, you can find it by K1x Lx over Rx, K2x Lx over Rx, K1 y Ly, K2y Ly. Because we do not have K2, so we can ignore this term and we have to find these values. K1x, we know 1, Lx is 6000 millimeters, Rx was something, K2x was 1.45, this is 6000 again, Rx, K1y is 1, Ly is 3000, and Ry was 102, I think. So we can calculate slenderness ratio in these three cases by this way. For example, this was 40, this was 45, this was 25. So we are going to use the largest one. So R would be the largest one, that will be our 25. The slenderness ratio of our section. So we have to take this slenderness ratio, go to compression members, and we have to check the KL over R at 45. This is KL over 45 and 5 CFCR would be 202.1. This is our 5 CFCR. So our capacity PC that is equal to 5 CFCR into gross area. So if you multiply 202.1 times 30,100, we check this from table. This one. So we can get the value by this. It would be in newtons divided by 1000 to get in kilonewtons. Okay, the last one is MC moment capacity. So for moment capacity, we have three cases. If our LB unbraced length is less than LP, if our LB is greater than LP but less than equal to LR. A third case is LB is greater than LR. What is this LP, LB, and LR? For example, this is our section. This is approximately how the capacity of section is going to vary. First, we have almost constant capacity, and we refer this as plastic region or plastic moment carrying capacity. This is up till LP. After LP, we have inelastic region. Here, inelastic buckling would happen, and this is up till LR. And after LR, we have elastic buckling. So first, we have to check our LB. LB is greater one of LX and LY. We have LX 6 meter, LY 3 meters, so LB would be 6 meter. The greater one of LX and LY. On breast length is 6 meters. We have to, and if we go to the column selection tables, for example, like this, then these values are directly given here. This is LP given for any for this section, LR given for this section. So we can see that our LB, this is 6 meter. If it is less than LP, this plastic movement carrying capacity, then our design moment phi b mn directly be equal to phi b mp. And phi b mp is directly given here. This one. So we'll directly use our design moment as this plastic carrying capacity. And this is also called C. This one design moment is MC, moment carrying capacity. If our LB is in between LP and LR. For example, if this was our section selected, our LB is greater than LP and breast length is 6 meter, it is greater than plastic length, but it is less than this LR. So we are going to use different formula here. We can check it from here. It is like phi b mn is equal to phi b cv into mp minus bf lb minus lp. We can memorize this, or it is also written here, I think. Yes, this one. Just multiplied by 5. 5b. 5b is 0.9. Bending. This is factor for bending. So multiply by 5 CB into MP minus BF, LB minus LP. LB minus LP. So all these values are all again given in that table. So we are given LP and LB here. LP and we know LB. LP is given in the table. BF is also given in the table. MP is also given. This 5B MP is given. So if we divide 5B MP by 0.9, if we divide 5B MP by 5 value, that is equal to 0.9. So we'll get MP value directly. So just divide this 5B MPX value by 0.9. We'll get this MP value here. Or you can use it like this. Multiply 5 inside. So 5B MN is equal to CB times 5B MN minus 5B BF LB minus LP. 5B MN, 5B MP we can get from here. We know 5.9 BF, we know table, and LP and we are also know. CB is equal to 1. We are going to assume it as 1. We are not going to do calculation for CB. Third case is LB greater than LR. So in this case, our formula would be 5BMN is equal to 5B SX into FCR. So SX is section modulus in the about X direction, and FCR is critical stress, buckling stress. So we have to get FCR from this long formula, this one. So we can use this formula, or this is its approximate one. We can use this bottom formula also. So in this one, we have to calculate RTS also. The RTS formula is given here. This one. First, we have to calculate this RTS. Then we have to put in this value and calculate FCR and multiply this FCR with a section modulus, and pi b will get movement carrying capacity if LB is greater than LR. So these three cases we have to be vigilant about. So this way we can get MC. So now we have all the values. We have to just apply interaction equation. Last, we have to just apply interaction equation. So interaction equation is also given here. So first we have to calculate PR over PC. If this is greater than or equal to 0.2 and if this is less than 0.2, there are two options. So if this is greater than or equal to 0.2, we are going to use this formula. PR over PC plus 8 over 9 MRX over MCX plus MRY MCY. And again, if it is less than 0.2, we are going to use PR over PC times PC plus MRX over MCX plus MRY MCY. And answer of any of this equation, which one is which one we are using, must also be less than 1.0. If it is greater than 1, then we have to revise the section. We have to go through this step again. Recognition factors. Again, take a higher section, calculate this B1, B2 again, and calculate the capacities again, and we have to check the interaction equation. We have to do these three steps again till the answer 1.0. It was written that answer can be up to 1.0099. If it is in between 1.0099, it is okay, but it cannot be greater than 1.01. It cannot be 1.01. If it is 1.01, fail. Okay. So any questions? This is the total question. We have no combinations, value of K, and this they have calculated P equivalent here. For first, this was P equivalent for first trial, this is P equivalent for final trial, and they are using this for converting, and this is capacities. V1, V2 is here, and finally they have checked fraction equation was a little bit high, almost okay. So we can fail this section and try again. Question.
In paper, normally, sir will focus on the analysis part, no? In paper, sir will focus on the analysis part.
Yes, most probably, because if you check the past paper, analysis part is, but design part is very much longer. We have only, I think, about maybe 15 minutes for this question. So you cannot do this. Because 30 minutes are for concrete, 15 minutes are for this, 5 minutes for axial column, and 10 minutes for. I think analysis part. Okay.
That's okay.
So So this the second part of circle is a very small part, so it is only line of base plate. So base plate is, for example, this is a concrete pad. You have to place a column in it, or a column on top of it. So we cannot place directly the column for just fail. So we place some base plate, steel plate on it, onto which we fix our column. For example, this is our column. We fix this column or weld this column to this base plate. This base plate is anchored in the concrete pad. The use of the base plate, why we use the base plate? I open the question. Only axially loaded base plate we have done up till now. Only axially loaded base plate. So for example, this is our base plate. We have some I section on it. It is W360 in 314 and steel is 836. FC dash of concrete pad below is 17 megapascal. A2 over A1 ratio and PU is equal to 5000. These values are, this is given data. A2 over A1, A2 is the area of concrete pad, and A1 is the area of face plate. So ratio of A2 over A1 they have assumed as 2. This is given. First, we have to find D and BF of this section. So we can go to column tables and find D is 399 and BF is 401 millimeter for this column. 316 to 314. So after finding this D and BF, the first step is calculate A1. We have to calculate the area of base plate. So there are three formulas given. We have to memorize these ones because they are not given in the LRT manual. I've searched, but I find those. They are not given. You can try. So formulas are 1 over A2, PU over 0.85 into 0.65 FC dash. They are almost similar, so we can easily memorize them. This is formula number 1. This or A2 over A1, PU over 0.85 into 0.65 C dash. Remember, there is no square here. This is square only in this portion. So if we are directly given the area of concrete is 3000 millimeter square, so we have to use this formula. If like this case, we are given the ratio of area, we are going to use this portion. Place ratio as 2 and place PU value 85.65 and FC dash value equate 8. Second formula is just the same. Just we have used A2 as 2. So we can get PU into 0.65 into 1.7 FC dash. We have used A2 as 2 times 0.85 is 1.7. So I can write it like this, that PU over 0.65 to 1.7 FC dash. This 0.65 is 5. We use 0.65 for special numbers, concrete numbers. So this was, and the last one is, we go here. Some formulas are given for base plate, but not, and these formulas are not given. At 333 here, 331. So last formula we can memorize or we can get named from this one. That the third area should be greater than this, T plus 18 and BF plus 18. So T plus 18, this is the minimum area. BF plus 18. Just multiply these two. This is the third area. So whichever is the largest of three, T1 is equal to largest. Whichever is the largest, we are going to use. Okay, so this is how we can calculate the area of base plate. After calculating area, we have to find its dimension B and N. This is a base plate, pose N, this is pose. So we have to find this values B and N. So simply, if it is said that we have to use a square base plate, if the base plate they have said that it is square, then simply B that is would be equal to N because it is a square base plate. That would be under root of A. Square root A would give you B and N. And round it up to 10 multiples of 10. Because this value would be high like 350 and 365. So we can round up 10 multiples of 10. And if they are written that economical or minimum, we have to select the base plate. The minimum base plate or economical is the same. So minimum size we can get by this formula. First we have to find x is equal to 1 by 2.95 d minus 0.8 bf, and n is equal to under root a plus x, and b is equal to a1 over n. So we can get x and a n and b from this. If it is written that we have to find the economical, so we can get x and b these formulas depending on the case. After this dimension are known, third step is to thickness of base plate. Thickness TP. The formula of TP is also known, given here. TP is equal to 2 times PU. TP is equal to L into 2 times PU 9 and F. As A36, the steel is A36, so Fy is equal to 250 megapascals. Pn we have calculated, Pu we know this one, L we do not know. L would be the largest of M and N bar. These three factors. N bar, the formula is directly given here. N bar is 1 by 4 D into BF. 1 by 4 T into BF. We directly know. Given here. M and N, they are not directly given here, but we can memorize from this one. That M is equal to this. I have memorized them like that. In M, we have to use N, capital N, minus 0.95 D. This first factor. 0.95 D whole divided by 2. 10. This is M. In N, we have to use B. B minus 0.85, 0.8 BF. 8 BF divided by 2. And you can just memorize this like this, that in N we use P, in M we use N, or P would always come with BF. P and BF would come together. Remember it anyway. This is how we can get M and N values, and N bar value, N bar formula is directly given in the LFD menu. So from this one, the largest one, we are going to select it as L and just multiply it to get thickness. So the last part for this is varying pressure. We have designed our plate, bearing a base plate. We have determined its dimensions. We have determined its thickness. Now we have to check whether it would support the given applied load PU or not. This is the last step. So the formula for PP is given this one. PP is equal to 0.85 dash E1, E2 or A1. Just like in PRC2. PP is equal to 0.5 dash A1, A2 over A1 root. And it should be less than equal to 0.85 FC dash A1 or this factor not be greater than 2. It comes greater than equal to 2, and this is limiting point. 0.5 into 2 means this one 0.85 FC dash. So this is PP, and we have to multiply this by 5 factors. It's also given here. 5 equal to 0.65. So 5 into 0.85, 5 into this. This is design capacity of our base plate. And design capacity 5 PP should be greater or equal to PU. So it is greater or equal to PU, then it is okay. Otherwise, we have to revise. Any issue in this? This was a simple code. First, we calculate area of base plate. From that area, we calculate the dimension of base plate, then the thickness of base plate. Finally, we checked whether our base plate was standing the load or not. Issue?
No, brother.
This was all for Rashid part. Is there any problem in this part?
Hamzira, brother, I have one question. That you have told that another method while we are finding the n and b
Yes, yes.
by using equation. At what times we should use that?
If
Yeah, this
they,
equation.
yes, if they have not specified that we have to use square, it is our choice. In that case, it is our choice. We can use square or we can use this. If they are specifically written that we have to find the economical base plate. They have used the word economical or minimum. If
Okay,
they
then
use
we
the
should
word
use this thing.
economical, that just means that we have to use the minimum dimensions of it.
Okay,
Yes,
brother.
with that. Okay, I'll stop the recording. We can discuss, sorry,